to either accept it or you're going to get booted. All right, he was booted, so maybe he'll come back. Okay. Great. Let's do this. All right, so for everyone that just joined, my internet is really flaky today. If I'm offline for more than like 5 or 10 minutes, I'll post on Piazza over my phone or whatever, and I'll just record it offline and I'll upload it, and then I'll do like lab office hours when my connection becomes more stable. And I'll post that on Piazza as well. Okay. All right. Neil is extremely excited. All right, let's go. Let's do this, everybody. We're going to talk about graphs. We're going to talk about some algorithms. It's going to be sick. Here's some things that you want to know. Yep. I'm sure y'all are on top of that. Project 4 should be out today. Or I think it should be out today if it's not already yet. But if it's not, then tomorrow for sure. And it'll be due the 22nd of June. We're almost there. We're going to talk about graphs and MSTs. And there's the handwritten problem at the end. Okay, so graphs, y'all have probably talked about this in the past before, in 203, or I forget, but you should at least have an idea of what they are. But this is our definition. We have a set of vertices and a set of edges, V and E, typically, as explained here. V is the set of vertices, E is the set of edges. And each edge is defined, each edge can be defined by the pair of vertices that it connects. So for example, we could have E1 equals, in this case, B1, B4. Can you all see the writing on the, like the red, this red writing here? Okay. Great. Yep. So that would be an example of what we have. So this is a graph. All right. Different types of graphs. We have directed graphs where the edges have specified directions. So this could be in any social media. You have directed graphs because you have people like following each other. So we could do something like this. Boink. Oh my gosh, why is it so slow? Okay, that's an arrow. It's going to this one. So there could be, you could have like reflexive graphs or whatever. Well, reflexive on itself, but you could have both ways directed on a directed graph. There are, like this, many examples of places you use directed graphs in outside of social media networks. In my research at the university, I'm using directed graphs to explain like plant-pollinator relationships. So directed graphs are very powerful. At least I enjoy them. Then we have undirected graphs where a connection implies some relationship. Thanks, Neil. Some relationship that is mutual. So we would all hope that if we are friends with somebody else, they are friends with us as well. So that graph could be undirected. And then we have undirected and weighted. We could also have directed and weighted, but essentially we just have the, that's not what I want. Anyways, these weights, these numbers next to the lines correspond to, like, here, we have the example of road networks. Like you could just give the length of road, that would be the weight in the graph. Things like this. Like if you wanted to do, you could do like flights and the cost of the flight in fuel or in dollars or whatever. It could be the weights, etc. So lots of graphs. Some just simple terminology. We have a simple path where a sequence of edges leading from one vertex to another to another with no vertex appearing more than once. We have a connected graph, which is a graph that satisfies the condition that a path exists between any two vertices. So from any vertex, you can get to any other vertex with a path length of 1. A cycle is a simple path from a vertex to itself with no edge appearing more than once, so you can make a cycle on the graph. Dense is the number of edges is close to the maximal number of edges. Can someone give me the big O estimate on the possible number of edges in a graph? Yep. Yeah, v squared. Right. And if you wanted to get a little more picky about it, you could do, that is the correct big O estimate. But as you may all know, it's n times n minus 1 over 2 v squared. So that's if a graph has O of v squared number of edges, then we call it dense. And if it has anything less than that, if you can define the number of edges with big O and less than v squared, then it would be sparse. Cost. Okay, graph representations on a computer are a bit different. You can't just draw circles and have lines between them, as I'm sure you all know after most of the semester. So we can have adjacency lists, which would be this option here, where you have a vector, it has a linked list or another vector or something coming off of it. For vertex 1, it's connected to 2 and 5, here and here. Vertex 2 is connected to 1, 5, 3, and 4, etc. An adjacency matrix is essentially the same thing, except you are explicitly defining what the connection between any two vertices is. So here you would, 1 is not connected to itself. There's no reflexivity in this graph, so it's a 0. It is connected to 2. It's not connected to 3, etc. This is a very convenient representation for weighted graphs, because instead of a 1 here, you could supply the weight. And these are very frequently used because there's a whole bunch of matrix algebra that you can use with these. It's very powerful. Yeah, so that's how you're going to see it. And this will come up in project 4, so good stuff to know. Okay. Neil's really spurging out. Can we stream this lab on Twitch? We could. Probably be more fun. Okay, so we're going to talk about sparsity and density and what that means for different graphs. I'll just give a few examples, and it should hopefully help this be a little more clear. So a tree, which is a graph with no cycles, does anyone have any idea whether this is sparse or dense? I wish we had a voting thing. I guess you all have the slides on your computers. It's maybe I don't need to ask the questions, but I'll try to encourage some participation. Okay, everyone says sparse. Yeah, it's sparse. How many? What is the maximum number of edges a graph can have with no cycles? Yeah, v minus 1, exactly. So that's O of v, and then O of v is less than O of v squared, so it's sparse. Okay, how about the internet? The vertices are each web page. The edges are links between the web pages. What do you think, sparse or dense? I mean, just think about if you go to Wikipedia, which are probably some of the more densely populated pages with hyperlinks. How many? Okay, y'all are saying dense. How many hyperlinks do you think a single an average Wikipedia page has? On the order of hundreds, probably, right? But what's the number of web pages on the internet? It's like billions, tens of billions. Yeah, yeah. Neil says a lot. Nice, Neil. Good job. Yeah, so there's a lot of web pages. So if you have if a very densely populated page of hyperlinks has maybe on the order of hundreds of hyperlinks on it, but there's billions of pages on the internet. What do you all think now? Is it sparse or dense? Yeah, it's sparse because, right, oh my gosh. It's sparse because it's not on the order of v squared. Like you're never gonna get, you know, a single web page connecting to the majority of the other web pages on the internet. Or anything definable in terms of v squared, right? Is that making sense? Okay, if anyone has questions about these, say so. Okay, great. How about, all right, now we have words in the dictionary are our vertices. The edges are U and V are adjacent if and only if they start with the same letter. So apple and alligator have an edge between them because they both start with A. Neil, he's such a spurred man. What do y'all think? Is this sparse or dense? So like apple is connected to every other word in the dictionary that starts with A. Dog is connected to every other word in the dictionary that starts with D. Okay, Eleanor says dense. I agree with Eleanor. Can anyone tell me what the number of, yeah, nice. Can anyone tell me what the number of, what the average number of connections each node will have in the dictionary or in the graph? Yeah, exactly. V over 26. Right. So, or the cardinality of V over 26. Yeah. Yep. So that'll, if you can define the number of connections in terms of V, and then that'll give you V squared since they're mutual. Okay, is this making sense? Are we good? These are, I mean, this is not particularly going to come up in Project 4, but a problem like this could be on the exam. Can you iterate the main difference between dense and sparse? Yeah, so we call a graph dense when you can define the number of connections in the graph in terms of V squared. So, or in terms of V, if you can define the number of edges connected to a single node in the graph, like the degree of a node in the graph in terms of V, then it will be dense. And also, if you can define the total number of edges in the graph as O of V squared, or like theta of V squared, then the graph is also dense. If it's O or theta of anything less than V squared, it's sparse. Does that make sense? Okay, great. So yeah, this is dense. All right, graph traversal, O of V would be less than V squared, yep. Graph traversal algorithms. So y'all have done a bit of this. We have depth first search and breadth first search. Depth first search, we use a stack. O of V for the degree of a single node. So if like sorry, I'm just looking at the chat. If the degree of a node is O or theta of V, then the graph will be dense. Or like if the average degree is O or theta of V of the degree of the node, then it'll be dense. But if the number of connections in the entire graph is O of V squared, then it's dense. Yeah. Yeah. Yep, no problem. Okay. All right, so graph traversal algorithms. Depth first search uses a stack. We visit child nodes before visiting sibling nodes. So I think about like a BST, and I think about like we go down a single arm of the BST, and then the next arm of the BST, and so forth, And so that is depth first search. Breadth first search uses a queue, and you're visiting siblings. So it's kind of like what you did in pairing priority queue when you needed to pop off the top. You would traverse all of the siblings, but instead of a traversal you'd be traverse all of the siblings, and then you traverse all of the siblings in the level under that, and then all the siblings in the level under that. And so it's breadth first search. It's like also called level order search. Depth first search is kind of like captain and treasure hunt. So you use both depth first search and breadth first search in the treasure hunt. The difference was a stack versus a queue. I think, couldn't the captain also use a queue? Yeah. So I think that I think like we tried to get you to do both. Yeah, by default captain is a stack. So by default, you're doing a stack depth first search in the treasure hunt. Okay. All right. Then there's a bit of code here that explains this. I'm gonna leave this to you. I mean, the code does what we just talked about, but if you feel the need to look over these, sometimes this is useful for exam questions, but we wouldn't make you write out depth first search or breadth first search. Maybe we'd ask you about a line of it, or we'd ask you like the general concept or situations in which you'd want to use one over the other, which we'll talk about in a minute. Okay, any questions before we move on to MSTs about depth first search and breadth first search? I'm going quickly over that just because I feel like y'all have already touched on quite a bit of that material. Okay. Yeah, if there are any questions, just post in the chat. I'm looking at it, so we will move on to minimum spanning trees. So really quickly, you have not done minimum spanning trees in lecture, correct? Oh, you did. Okay. Okay, great. All right. Perfect. I think I was going to look at the schedule of topics when my internet dropped, so that is why I did not know. Okay, great. So we're just going to review them, talk a bit about them, and talk a bit about like how the algorithms perform. Okay. So a subset of a graph G that contains all the vertices in V is connected and does not have any cycles is what we call a spanning tree. It spans the graph. They're very useful for many things, like mostly in networking technologies. But yeah, they're very useful. So the spanning tree, this is not true. The minimum spanning tree of a graph G that has the lowest total cost is the tree that has the lowest total cost. This line is messed up. We could just write here that has the lowest total cost is the MST. This means that an MST is a subgraph of G, contains all the vertices in V, is connected in acyclic, and the edges whose weights have a smaller sum. It contains all the edges, the sum of which are smaller than any other spanning tree. Okay, so here's a graph, and there's different ways to connect it into a spanning tree. This one, for example, is a spanning tree, but this one is the minimum spanning tree because we're still connecting all 4 nodes, but instead of this 16 weight, we have this 8 weight. Okay, great. So a couple different ways to get a minimum spanning tree. Can anyone post in the chat about what the, can you explain this cost concept again? Okay, so before that, let's talk about cost. So in our graph, we have edges, and we're assuming that when we're dealing with MSTs, the edges have weights, because if they didn't have weights, then it's trivial to compute an MST because everything, you would just treat everything as if it had weight 1, and then just find any spanning tree of the graph, right? So yeah, the weight can be an integer, it can be a floating point number, a real number, it could, it's arbitrary. It could be an unsigned integer. It could be a Python dictionary. All that matters is that you have a like comparison between the types, right? So as long as you can say, for example, like 8 is less than 16 here, it could be a class. As long as you can say that one instance of the class is less than another instance of the class. So as long as we can have some sort of relationship, like we'd rather have 8 than 16, then we're interested in using an MST. Okay. You would have to define, less than for Python dictionaries on your own. Okay. So we have. Does this make sense at least? The cost, why we're concerned about cost and weight. Okay, great. Can spanning trees have cycles? No. Spanning trees, by definition, are acyclic. They will always have v minus 1, cardinality of v minus 1 number of edges. It is purely connecting all of the nodes in the graph. So no cycles. Yeah. Lowest weight is lowest cost. Yeah, so I'm using weight and cost interchangeably here, I guess. I'm referring to the same thing. I'm referring to this number that's associated with the edge. The lowest weight indeed is the lowest cost. In fact, trees in general are acyclic. That is true. Okay, great. I'm gonna move on to prims. So can anyone remind me what the runtime complexity of prims and Kruskals is? With no fancy like alternative algorithms, just bare bones vanilla prims and Kruskals. Yep. So n squared v, yeah, exactly, v squared. Yeah, so prims is v squared. Kruskals is also v squared. The constants are a little different. You can define it a little differently depending on how you what parts of your graph you're interested in, basically. So if you know in your graph, if you know that your graph is dense, then it's better to use prims. If you know that it's sparse, it's better to use Kruskals because you can take alternative strategies and one will work better than the other in different cases. But we'll talk a bit about that. All right, so Prim's algorithm is a greedy algorithm. It separates vertices into two groups. The innies are the vertices that are in the partial MST at any point in time during the algorithm. And the outies are the vertices that have not been included in the MST at that point in time during the algorithm. So what we do is we just find the nearest outie vertex iteratively, and then put it into the MST and do it again. It's best for dense graphs, as we'll see in a second. Okay, so here's just a quick example. We have these 4 nodes on the inside, and we're just going to evaluate what is the closest. So we're going to look at I'm going to like slash them, I guess. So we'll look at that one. We'll look at this one. We'll look at that one. We'll look at that one. Look at this one. We'll look at that one. We're going to look at this one. That one. Come on. And this one. Because these are all the edges that are connected to our current partial MST. We'll go over how we begin the algorithm in a second. Yeah. So we're just midway through the algorithm at this point. We're just stepping in at some arbitrary step to look at how it's working. So we're going to look at all of these edges with the red crosses through them, because those are the edges that are connected to our current MST, and we're going to find the lowest weight or cost equivalently among them, and we're going to add the vertex that is connected to the other end of that edge to our MST. So that will look like this. We can go down. Okay, great. We're looking at all of those edges, any edge that's connected. I think this one should also be highlighted. Points to the inverted. Okay, yeah. All right. So I'm wrong. The yellow is highlighting the closest, but then why are these? Yeah, all right. This slide isn't making a whole lot of sense. But like I said up here, we're looking at all of these edges, and we are going to choose from among them. So we found the closest one was this one. We're going to bring that to be part of our MST, and then we're going to iterate. Assuming blue is lowest weights, draw this. You want weights, basically? Scroll up. Okay. You want me to my previous question. How do you determine the blue is in the MST? The weights aren't given, so how do you know blue? So what we're doing here is someone has generated a partial MST for this graph, starting from one of these 4 nodes. We are stepping in at some point, a few steps down the process, and we're just going to look at a single step in the algorithm. So we only know that blue is the MST because I'm telling you that blue is the MST up to this point. Does that make sense? Okay, I'll keep going from there. Okay, so we add the closest vertex to our partial MST. And now we're going to run through all of the vertices. We're going to update the weights that, we're going to, if we look previously, before this one was in, we were not looking at what the weight is to get here. And we were looking at this edge to get to this vertex. But once we add this vertex, we can now use this edge weight to get to this vertex, and we can use this edge weight to get to this vertex. So maybe the weight is better, maybe it's worse, but you obviously you're always going to take the best weight, but you can update them if need be. Okay, and then you just repeat until all of the vertices are in the MST. Okay, so here's just like some prose pseudocode. We're going to begin with a random node, mark it as the partial MST for now, innies. Until all the vertices have been marked as inside the partial MST, we're going to choose the vertex X that is not part of the MST, and it has the smallest distance from any vertex that is inside the MST. We'll add X to our MST. We're going to keep track of its parent so that we know what edge connects it to the tree. And then we're going to update the weights to any vertex that it's connected to. And I'm going over this so many times because this is, you will be writing prims in Project 4. Don't write Kruskals. You'll be writing prims in Project 4. And it's really important that you understand all the steps that prims takes. So we're going to go over an example from the beginning this time, just to make it abundantly clear to everybody how this is working. And I am still watching chat, so just let me know if you have any questions as I go. Okay, so here we're just marking vertex 1 as the initial starting point of our MST. It could be any vertex, it doesn't matter, but we're just going to choose one and we're going to go with it. So we're taking 1. All right, is it inside the MST? True and false significant, yeah, true and false. Inside MST is K here, K sub V. We have V1 is inside, everything else is outside for the moment. How far is it from the nearest in node? It's 0 because we didn't have to travel to get there. We're just starting there. Everything else is infinity at the moment. We haven't updated anything. Okay, which MST node is closest? This is like the parent, and it's how we determine how we added that node into our MST. So these get populated once a node joins the MST. Okay, so first thing we're going to do is we're going to look at any node that V1, because it's the node we're starting with, is connected to, so V2 and also V4. And we're going to update the weights of those, the distances, in our table with the weights of on the graph. So V4 will be 7 here, and V3 will be 13 here. And we're going to mark that as coming from V1 because that is the connection we're using. Okay, let's keep. Does this all make sense? Right now, what is our minimum spanning tree? Right now, it's only V1 because that is the only node that is inside the MST. All we've done is update weights, our understanding of what nodes we can get to. So the next step is going to be adding 1. I'll be out in a minute.
Can I get your adapter for the HTML?
Sure. Just a second. Sorry about that. Okay, so the next step is we're going to find the minimum distance, and we're going to add that node into our MST. So what can someone post in the chat what node we will add next? Yep, we're going to add V4. Yeah, exactly. Because it's 7 is less than 13. Okay. All right, so we add V4. Now, once we have V4, we're going to find all the nodes that V4 is connected to. So V6, V3. We're not going to update V1 because it's already inside of our MST. So we're going to update v6, v3. We're also going to update v5. Those are the 3 edges that we're concerned with. v4 is currently, yep. So it was outside of the MST. Now it's in the MST. We've added it. We're updating weights to v3, v5, and v6 because those are the nodes that v4 is connected to. Okay, glad to see it's making sense. All right. Okay, so what's the next step? Someone tell me. Look around v4. Yep, so we've just looked around v4. We've updated the distances to the nodes it's connected to. Ron says we're going to add v6. That is correct. Yep, we look at the minimum of this column in our table that is not currently part of the MST, and we take v6 because 2 is the least of anything in the column. So v6 will be added to the tree. Great. Okay, v6 is not connected to anything besides v4, and v4 is already inside of the tree, so we're going to not update anything. Great. All right, now we're going to add v5 because out of the, so look at all of the weights in this column for nodes that are false for inside the MST. So we have 13, we have 6, we have 4. So we'll add v5 with weight 4 because that's the least. I'm going to mark that as true. And we're going to update the weight to v2 with this 5 distance here. The parent will be v5 because that weight is coming from v5. So it's important not to think about this as like you're hopping around on nodes, because you can add the next node from any node in the MST. So this is a huge problem I see with Project 4 every semester that I teach, is that people assume that now once you've gone to a new node in Prim's algorithm, then the next node you'll add is from that node or from the last node or something like that. It's just any node that you're possibly connected to. So that's very important. Okay. All right. And we'll add v2, and then finally we're going to add v3 because it's our last option. Okay. Does that make sense to everybody? Does everyone understand how we got our MST? Yep. Okay, great. I'm going to move on unless I see questions. I'm going to move on, and then if I see questions, we'll return. Okay. So here's our MST. And it's defined, is our MST going to add everything? Yeah, so we just, we have all the vertices inside the MST. Yep, MST will always, by definition, it spans the entire graph. So it will always include all of the vertices, and it will always have the cardinality of v minus 1 edges. Yep, okay. Great. So it's also important to note that the MST is purely defined in this table, right? Like we're not building an additional data structure for our MST. We're not going to define like a new matrix or anything. It's only defined within this table. But here is the drawing that accompanies it. Okay. Here are the complexities. There's a bunch of ways to get it under v squared, but just don't worry about it. Just use the one that we've described here in Project 4, and that's like, yeah, it'll work, and it'll be under time. Okay, Kruskal's algorithm. Also a greedy approach. Are we supposed to leave PV blank for V1? So the question is this supposed to be, is the parent of the original node supposed to be blank? Yeah, I mean, you could set it to some placeholder value, -1, or yeah, you just want to make sure that you know that is the root of the tree, basically. You could set it to itself even. You could set like this could just be v1 here, and then you would know that once v equals p sub v, then you found the root or whatever. But yeah, right. What goes here is just to let you know that that's where you started. Okay. All right. We did that. We're going to here. So Kruskal's algorithm. Sorry, Kruskal's algorithm. I like to think of prims as we're sort of dealing with vertices. Kruskal's you're sort of dealing with edges. We're gonna maintain a forest, and eventually that forest will coalesce into a single tree. But we'll be picking out edges that we think are good as we go. So we're just gonna take the cheapest edge in the graph as long as it doesn't form a cycle in our tree. And then we just keep going until all the vertices are in the set. All right, so let's try it out. Okay, here's our initial graph. I think we're starting with V6. Yeah, okay, we're starting with V6. Oh wait, no, this is this is what I'm telling you. We're not thinking about this as nodes. So there's no need to start anywhere. Can you re-explain cycles? Yes. So here, V4, V2, and V5 have a cycle because from V5, I can get back to V5 on a path that only includes each edge once. So it wouldn't be a cycle if I had to go, V4 and then V2 and then V3 and then V4 and then back to V5 because I would include this edge twice. So V2, V3, V4, V5, V2, V4. Yeah, that's a cycle. Yep. 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 I think, yeah, it's fairly intuitive, but yes, that is a cycle. Just anywhere that you could keep going, or yeah. Okay. So first thing we're going to do is take the cheapest, just find the cheapest edge, right? It's the first one, so there's definitely not going to be a cycle. Let's just take the cheapest edge. That's going to be V4 and V6 here. Now these are both in our MST. So I think I don't like this slide because it makes it seem like V6 is in the MST right now. It's not. Nothing is in the minimum spanning tree yet until we add this edge, and now both of those nodes are in the minimum spanning tree. Okay, someone tell me what the next edge we're going to add is. Either the weight or the two vertices or whatever. V4, V5. Yep, exactly. This is confusing. Okay, great. So if we're adding edges, where do we start? Right, that's what I'm saying. There's no starting. So you have like some table or adjacency list or something that's describing your graph, and you're going to go through and just find the cheapest edge, the edge with the lowest weight. Yeah, so it's just all you do is you start here. Nothing is inside the MST. You look at 13, look at 5, 5 is less than 13, 7, 15, 4, 4 is less than 5, 6, oh, 2. 2 is the least cost in the entire graph. So we're going to take that edge to be part of our minimum spanning tree. So we're thinking now of the edges, adding edges, which adds vertices, instead of adding vertices directly. Sorry. Does that make sense? Yeah, the V6, V4 connection. Yeah, exactly. It's just because it's the cheapest one. Okay. So we add that one. Now, I think as people said, we're going to add the V4, V5 edge because now 4 is the cheapest edge in the graph. And we know that this edge is not going to add a cycle. So that is what we will add next. Okay, what's next? Okay, I'm seeing some varying answers here. Okay, so I think it's going to be V2, V3. And this is where it starts becoming a bit different than Prim's, right? Because we're no longer connecting the next edge to our current tree. We just found, all we did was we said, okay, these three are in our minimum spanning tree. What is the next cheapest cost of any of these other edges? 15, 7, 6, 5, and 13. And let's just take the cheapest edge within those, as long as it doesn't add a cycle. So you just grab random unlinked edges. Yes. Well, not necessarily unlinked, but just as long as the edges don't add a cycle, then we're good. Yeah, so we're going to take V2, V3 because 5 is the cheapest remaining edge. If they add a cycle, then we'll see that in just a second. Great question. Okay, so what is the next one? The next V3, V4. Yep, Ron's got it. 6 is cheaper than 7, 15, and 13. So we'll take that. Now we've connected the two separate spanning trees, which doesn't have to happen, until the end of the algorithm even, but at some point you'll be connecting all of them. Doesn't it not take the cycle anyways? Well, so we don't think about, like, the algorithm doesn't consider, right? Because I see what you're saying, right? You're saying, like, 7 is the next cheapest edge, but V2 and V4 are both in the minimum spanning tree already, so we wouldn't consider it. That's valid. You could make that check if you wanted, but also 7 won't be added because it'll create a cycle. We are about to talk about it, yeah. So I think, I guess what I'm saying is you don't have to consider. Do you have to consider? Yeah, I mean, I think, let's see. I think it comes down to an implementation detail, whether this would be rejected if it's a cycle or because it's connecting two nodes that are already inside the graph, basically. It could be either. Going back to Prim's algorithm, if it's a cycle, do we have to handle it? Prim's won't add cycles because you're adding vertices, not edges. So there's no, at no point would you add a vertex that's already inside of the. But Kruskal's can add a cycle. Yeah, that's good. Okay, we don't connect the edge with weight 7 because it would create a cycle, or as Ron is saying, for the reason that it could create a cycle, that it would create a cycle, or for the reason that V2 and V4 are already part of our minimum spanning tree, we're not going to take it either way. Okay, and then finally we're going to connect V1, and there's our MST. Okay, questions about that? Yeah, this edge is not doing anything for us. It'll cause a cycle, and also we have all the vertices inside of our tree at this point. Yep, either one. I mean, when the algorithm's done, there's no need to go any farther, right? Because the condition on your loop in this algorithm would be while you don't have enough nodes in your spanning tree. Yeah, okay. How many is enough? Well, enough is the cardinality of V, because you need all of the nodes in the graph to be in the tree, because it connects the entire tree. Or it connects the entire tree. Okay, so say 15 didn't cause a cycle, what would we do? We're not going to do anything because it's connecting two nodes that are already in the MST. So like we're just not even going to consider it because we've already connected those vertices. Yeah, they're already inside of our tree. Yeah, right. The edges don't want to keep connecting. I mean, there's just no reason. Okay, I'm going to go on. Yep. All right. So here's one way to do it. Sort edges by weight in O E log E time. And then, so this is why Kruskal's is good on sparse graphs, because if E is small, then E log E is pretty good. So then we can use a disjoint set data structure like union find, which I think you've done, to keep track of the vertices in each component. We do 2 find operations and up to 1 union, and that's basically constant time. Union find is not on P4 or final. It's not going to be on project 4. There could be some questions on it in the final. Okay, so the total time complexity is O of E log E or O of E log V, depending on which is larger, basically. Yeah. So you want to use Kruskal's in cases that basically you want to think about your problem, and you want to think about the structure of the problem, and think about which algorithm would perform better given that structure. So in this case, in project 4, your graph is dense, so you would use Prims because it's better for dense graphs. If you had a sparse graph, if you were thinking about trying to create an MST of the internet or something, then you would think about using Kruskal's. I wouldn't worry about any disjoint set data structures other than union find. I mean, there are plenty of, how do I want to say this? Union find implements like find and union, which are like, those are the 2 operations that you want to do on, if you're thinking about like multiple disjoint sets, but any data structure is a disjoint set with other data structures, as long as there's no like references and pointers and stuff. So I think it depends on what you're asking about, I guess. But yeah. Okay, modifying an MST. So we just want to think about a few cases in which we have an MST and someone updates an edge weight, and what do we have to do for our MST? So the edge is in the MST, you're decreasing the weight. It's not in the MST and you are decreasing the weight. It's not in the MST and you're increasing the weight, and it's in the MST and you're increasing the weight. Okay, let's start out. Okay, so first one, the edge is in the MST and we're decreasing the weight. What do you think? Do we need to do anything? First of all, so question 1, does anything need to change? Nope. Yeah, we're good, right? I mean, we're just making our MST even better. We're saying that instead of a weight of 8, in this example, it'll be a weight of 3. So we're just decreasing the cost of our spanning tree. Is there a function to decrease the weight? I mean, we're not even talking about code. Weight minus minus, yeah, exactly. So yeah, we don't have to do anything. We're good. All right. Great. Edge is not in the MST, and we're decreasing the weight. So we're taking that edge, and we're going from 9 to 1. Can the MST, do we need to do anything? First question. Do we need to do anything? Make sure you push back the lowest one. I'm looking for more of a yes or no here. Yes. Great. Thank you. Yeah, so we now have an edge that is lower cost than it was before, so we need to reevaluate what we're doing for our MST. So in this case, it's added to the MST, and here's a way to decide whether we add it or not. We add the edge whose weight was decreased to the MST. So you just, first thing you do is you add this edge that decreased from 9 to 1. And now we've got exactly 1 cycle. We know that we have 1 cycle because we started with the cardinality of v minus 1 number of edges. We've added a single edge. There are now v edges. We know there's a single cycle in the graph, at least 1 cycle. But it's an MST beforehand, so we know there's exactly 1 cycle. And now we remove the edge in this cycle that has the highest weight. And you can do that using depth first search or breadth first search with O of V complexity. Does that make sense? It's like it's going to rain here in Ann Arbor. It's raining. All right. Edge is not in the MST, and we're increasing the weight. Do we need to do anything? Nope. Yeah, this really doesn't affect anything, right? The MST isn't getting better. It's staying the same. Something that's not in the MST is getting worse, but it doesn't matter. Okay. All right. We're good. Edge is in the MST, and we're increasing the weight. Do we need to do anything? Yep. Yeah. Yep. We need to do something. Well, we might need to do something, right? We at least need to check if we need to do something. So we need to do something. Yeah, we're going to have to, here we go, yes. How can we find the new MST? We're going to remove the edge whose weight was increased from the MST. See if it's higher than a different edge. Yeah, we need to go find if there's a better connection, we need to find the connection. And we want to find the lowest weight edge that connects the two components. So we now, right, if you have an MST, you remove 1 edge. Now you have 2 connected components, and you want to find the cheapest way to connect them. And that's what you'll do here. And you can do that by breadth first search or depth first search in O of the number of edges amount of time, which makes sense. Okay. Are we good? Did that make sense to everybody? Yep. Okay. Then the last thing we have to do, well, last thing you have to do is the handwritten problem. Does anyone have any questions before I'm done? I'm happy to help or talk about whatever. can I go over the last case again? Yes. Handwritten Lab 9 is due, what does it say on Gradescope? I will do the last case. Let me just check Gradescope real quick. Nick, I think Nick is here. Does Nick know? Not on Gradescope as of this morning. Okay, I'm gonna put it up if it's not. Do we need to know how the code works behind modifying an MST? No, you're not gonna have to modify an MST. Okay, Neil says the Gradescope is up. I'm gonna trust that it is. All right. Great, so let's talk about this last case really quickly. I'm assuming that you're wondering about how you find the new edge. So we have these, remember, two connected components that we want to connect in the cheapest way possible. We're going to find a new edge in O of E time by traversing through the components that we have using a breadth first search or a depth first search. We can build two hash tables out of those components. So we're looking at the weights connecting any of those pieces. We found the shortest edge whose ends are in opposite components, right? So the cheapest cost edge whose vertices are in different hash tables. We have O of 1 time per edge for hash table lookup, so that's why we can do it. There's an open AutoGrader submission, but it's not in the lab assignment PDF. There is a coding part to this lab. There should be a zip file on Canvas. Or am I wrong? Let me open up Canvas. It might just be that the zip file is not published yet. Oh my gosh. My computer is so slow whenever I'm in a video meeting. Let's do that. You don't see a zip file. Okay, I need to publish that. Let's just do it now while I'm here with you all. Yeah, honestly, I mean, like the code that you would need to understand from this entire lab is the prims. If you can understand prims, then you'll be all right. Can you build your own AutoGrader? You can do whatever you want. Okay, unless you have questions, you can feel free to head out. I'm happy to keep answering questions. I'll stay on as long as I'm, uploading the files and such. But I think we're about done. Where's the Lab 9 computing survey? No, I didn't see that. Let me look at, I looked at the assignment this morning. I didn't see a computing survey, but let me see. What do you all think? Is it smart to go for a run during a thunderstorm or not a good idea? No chance. Can we talk about Prim's algorithm complexity? Yeah. Go for the run. Yeah, I like running in the rain too. I think I probably will. Okay, I see cycle.cpp and cycle.h that are both published in Lab 9 on Canvas. Do other people see that? Yes. Those are for the, oh, that's right. I'm sorry, yeah. Okay, then I think I need to upload the thing from Drive. Okay. I'll do that after I get off the call because my computer's just being really slow while I have while I'm doing this. So I'll do that as soon as I'm done talking to you all. Okay, so someone said, can we talk about the Prim's algorithm complexity again? Yes, definitely. Let's go to Prim's algorithm. This slide, I'm assuming you're talking about, Eleanor? Eleanor, are you still there? Yes, okay, great, sorry. Mainly about how the complexity changes with a binary or Fibonacci heap. So binary heap, like these are all very like specific settings that I think you'd still be interested in the structure of your problem and why, you'd have to justify to yourself why you would be making these changes. But you would use an adjacency list as the graph, and then you can use a binary heap to determine the next vertex to add instead of doing like a linear search. Then it's log n to find log n to pop out of the binary heap, which would be log v in this case, which is where this log v comes from. Yeah, I mean, I've never used a Fibonacci heap. I'm not totally sure what it is. I don't think you're not going to have to know. If you are curious, I would go look at the Wikipedia page for Fibonacci heap and think about how that could help you add the next vertex. But that's not something I've dealt with before. I would not suggest trying to use either of these methods in Project 4. This one is perfectly fine. It will be easily well within the constraints. This is the solution. This is the instructor solution that we use. So I'm definitely doing a lot of hand waving here, Eleanor, but I hope that when you say this one, do you mean yeah, I'm sorry, the first one. Yeah. Yeah. The first one is the algorithm that we used in the slides when we were doing like the table and everything. For prims, it's impossible to construct a cycle because once we add a node to the MST, we mark it to true or visited or within the MST. Yes, exactly. Then there's no reason to return to that node in the future, so we'll never get a cycle. Y'all are getting a little feisty in the chat. asking about research. I'm fine with waiting if there's questions about lab, though. How about email me and we can set up a time to talk if you want. Okay, great. Does anyone else have questions? Okay. I don't see any other questions. As soon as I sign off, I'm going to begin to upload the YouTube video, and I'm also going to be uploading the code starter files to Canvas. So that should be, 10 minutes. You should be able to find the starter code. Last question. All right, what's up, Neil? Yep, no problem. Nick, if you're there and listening, I really appreciate you coming and being able to bail me out if my internet went down. DT has just been turning my power on and off all day for seemingly no reason. Okay. All right. I am going to leave, and we're going to stop the recording.